Hello, good afternoon everyone. Good evening everyone. Good evening Ganesh, Chief of the God, Nisha, Leela, Pratyusha. Good evening all of you. Good evening. Good evening and welcome to another session of quantum chemistry. Welcome to another session of quantum chemistry. Alright, the English version of quantum chemistry. In the last class we discussed what simple harmonic oscillators are. In this class what we are going to discuss is the rigid rotor system. Okay, in this class we are going to discuss the rigid rotor system. Okay, it's a very important system because this system marks a transition from the Cartesian coordinate, meaning x, y, z coordinates, and we transition from that system to something called as the spherical or the polar coordinate system, where the variables being used are r, theta and phi. Okay, the variables that we use there are r, theta and phi. Okay, good evening Ganesh, good evening everyone, good evening everyone. Okay, so rigid rotor, what do you mean by a rigid rotor? Let's start with that. Let's start with what we mean by a rigid rotor. Okay, so rigid rotor systems means, suppose you have an object or a particle rotating around a specific axis. Okay, suppose you have a object or a particle rotating around a specific axis. Okay, so what we are going to do is, let's keep this particle here. Okay, so we have a particle which is rotating around an axis. Okay, this is the axis of rotation. What you can see here is the axis of rotation. And let's assume that the radius is r. Okay, so if you have a particle which is rotating around an axis, it is always at the same distance from this particular axis, which is radius r. And when that happens, instead of x, y and z, which will complicate the equation because it's an equation of a circle, you will get a quadratic, which is much tougher to differentiate or solve the Schrodinger equation for. So there is an easier version of the Schrodinger equation that we can use for these rigid rotor systems. Okay, hello Chief of the God, hello Akshay, hello Shabina, welcome to IFAS, all right. So I think now officially we are I think out of the Diwali season, right? And now it's time to really buck up and start preparing very well, start preparing in the earnest for our CSIR NET and GATE entrance exams. All right. Okay. So I hope all of you are sharing the link of this video with all your friends. If possible, you are posting it on your social media, if you're posting it on your WhatsApp status, so that everyone knows that we are back after Diwali. The English version of the batch is continuing after Diwali. All right. Yes, thank you so much, Leela. Leela is a very good friend of ours. I really like her enthusiasm. All right, because she regularly shares our link, she likes our sessions. And she always sends her love in the comments. Her love is visible in the comments. All right, and I'd like all of you to really emulate this. Okay, Chief of the God is here after a long time. I think after a long time, meaning after his Diwali break, he is back. He is back with a blast on IFAS chemistry and is here to learn quantum chemistry with us. He is always a very curious student, right? Devendra is a very curious student. Gopal is asking CSIR NET result. Okay, so the CSIR NET results were expected before Diwali, but unfortunately they did not release it before Diwali. Now we'll have to wait it out. I am guessing that if not by this weekend, in the next week definitely these results are going to be out. Okay, typically, good evening Pooja. So typically what we have seen is these results are out on Saturday evening or Sunday evening. So let's hope that this Saturday evening we will get our results. Okay, we will have our results in our hands also. Okay, good evening Pooja. Good evening Gopal. Okay, so let's continue with our rigid rotor system. Let's continue with our rigid rotor system. And if you want to find out the rigid rotor system, what you will notice if you want to calculate this is inside the potential is infinite. Okay, outside also the potential is infinite, but on the ring, if you look at this particular ring, on the ring potential is 0. Potential is 0 on the ring. Okay, just like particle in a box, potential was 0 inside and infinite outside. Here the potential is infinite inside, the potential is infinite outside. It is 0 on the ring. It is 0 on the ring. Okay, that's the main difference here. That's the main difference that you will find in these cases. All right, so this is the rigid rotor system. Okay, this is the rigid rotor system. Now, in order to make the equations easier, in order to make the calculations or solving the Schrodinger equation easy, what we have to do here is we have to move from what we call the Cartesian coordinate system, or the x, y, z system, and the polar coordinate system, meaning the r, theta and phi system. Okay, the Cartesian coordinate system and the polar coordinate system. Okay, so what is the difference between these two? Now, if you look at these two coordinate systems, they actually, the axis will look similar. Okay, the axis might look similar, but they actually mean completely different things. They actually mean completely different things. Okay, for example, here the axes are x, y, or rather this should be x. Hang on. The convention is that this axis should be the x-axis, that should be the y-axis, and that should be the z-axis. Now, suppose we want a point here. Okay, we want a point here. We want a point at this position. Okay, we want to talk about a point which is at this particular position. Okay, we want to talk about a point which is at this particular position. All right. What you can see about this point is you can drop perpendiculars on the x-axis and the y-axis. Okay, you can drop perpendiculars on the x-axis and the y-axis. I don't think you can see these. I'll just use a different color here. Okay, you can drop perpendiculars on the x-axis and the y-axis. All right. So you have an origin here. You have the origin here. Now, when we look at this particular graph, this point, if I draw perpendicular on the xy plane, and if I drop perpendiculars on the x-axis and the y-axis, these will give you the x, y, and the z coordinates. Okay, so the z coordinates are essentially distances from the x, y, and z axis. Okay, they are the distances from the x, y, and z axis. All right, is this clear? Is this clear to all of you? So what the Cartesian coordinate system tells us is what distances is this point from the three different axes. So all you have to do is you have to drop perpendiculars from this point on the x, y, and the z axis. All right, and you will get the three coordinates. Okay, so this is a system that you know very well. Okay, this is a system that you have studied a lot of times. Now, let's look at the same point, but in the polar coordinate system. Let's look at the same point, but in the polar coordinate system. Now, this will have coordinates r, theta, and phi. Now, how do you get to these coordinates? How do you understand these coordinates? So let's try to understand those. Okay, let me drop a perpendicular from the y-axis and along the x and the y directions as well. Okay, so this is still the x-axis, this is still the y-axis, this is still the z-axis, but now there's a difference that we see. If you draw this line, if you draw this line, okay, this line makes two different angles. Okay, this line makes two different angles. One is the angle with the z-axis, and that angle is called as theta. One is the angle with the z-axis, that angle is called as theta, and another is the angle with the x-axis, that angle is called as phi. Okay, that angle is called as phi. Whereas if you now look at the distance, of this point from the origin, that distance is r. Okay, if you look at the distance of that point from the origin, that distance is r. Okay, now what this means is, in order to reach this point, what we will do is, first of all, what we can do is, this is the z direction, we will tilt along the z direction, then we will rotate along the by making an angle with the x-axis, and then we will go a certain distance, like for example, you must have seen that in wars there are cannons, right? You've seen cannons. What the cannons do is, they actually move up a certain distance, they point towards the target, and then they shoot. Okay, so when they are moving in the vertical direction, that is the angle theta that they are changing. When they are rotating in the horizontal direction, that is the angle phi that they are changing. And the distance that they are talking about, that distance is this value r. Okay, so it becomes easier. All right, now I'm not going into why it becomes easier, because the equations are pretty long. All right, the equations are very complicated, so we are not even going to go there. But one simple thing that I can tell you is that if you solve using the polar coordinate system, instead of x, y, z, if we go to r, theta, phi, calculations become simpler. Okay, calculations become simpler. I'm sure that I'm not saying that the calculations become shorter. I'm not saying that the equations become smaller. I'm saying calculating becomes possible. Okay, with x, y, z, it's much more tougher than with r, theta, phi. R, theta, phi can give you solutions to the Schrodinger equation. Okay, so now for that, what happens to the Hamiltonian operator? Okay, so first of all, let's look at what x, y, and z are in terms of r, theta, and phi. Okay, now if you want to write x is r sine theta cos phi, y is r sine theta sine phi, and z is simply r cos theta. Okay, this is how you convert from polar coordinates to Cartesian coordinates. Okay, but what we want to do is, we want to go the other way around. So r comes out to be square root of x square plus y square plus z square. R comes out to be the square root of x square plus y square plus z square. Then if you want to calculate theta, theta is simply cos inverse of z upon r, whereas phi is tan inverse of y over x. Okay, now questions on these formulas, questions on these 6 formulas are very rare, but you can see questions like this in the set exam. So if you go and observe the set exam questions or even the TIFR exam questions, you have questions on these formulas as well. So this is from polar to Cartesian, and this is from Cartesian to polar system. Okay, polar to Cartesian and Cartesian to polar system. Okay, now if we want to solve the Hamiltonian, using the polar coordinates, okay, if you want to solve the Hamiltonian using the polar coordinates, what you will have to do is reduce the Hamiltonian in terms of polar coordinates. So Hamiltonian is minus h cross square upon 2m del square, okay, which comes out to be minus h cross square by 2m d2 by dx2 plus d2 by dy2 plus d2 by dz2 plus v plus v. Now this del square that was del 2 by del x2 plus del 2 by del y2 plus del 2 by del z2. This is the Cartesian system. This is the Cartesian system. Okay, now what happens in the polar system? What happens in the polar system? In the polar system, the Hamiltonian becomes minus h cross square upon 2m r square. Okay, or in fact you won't even get this small r, you will actually get the capital R, which was the radius, into del 2 by del phi 2. Okay, this is the Hamiltonian that you get for the rigid rotor system that we saw earlier. For this system where the radius is capital R, for this rotational system where the radius is capital R, this is a particle of mass m. This is a particle of mass m. Okay, in fact, in order to avoid confusion later, let's write this as capital M. Let's write this as capital M. Let's write this as capital M. Okay, in order to avoid confusion. And for this, the Hamiltonian comes out to be like this. Now, do you have to remember this Hamiltonian? Not really. Okay, you don't have to really remember this particular formula. Just remember that you have only phi dependence. Only phi dependence. You don't really have to remember this formula, but remember that the Hamiltonian only has phi dependence. Okay, which is why when we write the wave function later on, you will see that these values or the wave function has only the variable phi. There is no r, there is no theta. Okay, r and theta will be absent, only phi will be present. All right. Is this clear to all of you? Is this clear to all of you? If you want, just take a screenshot of the screen. If you want, take a screenshot of the screen. Just take a screenshot. If you want, take a screenshot of this particular slide. Take a screenshot of this slide. Okay, done? Okay. Now let's see what the wave functions are. Let's see what the wave functions are going to be like. Wave functions. And this is the 2D rotor that we are talking about. We are only talking about the 2D rotor. Okay, 2D rotor, this actually means particle on a ring. Okay, this is also called as particle on a ring. Okay, this is a particle on a ring. What does that mean? Okay, Pratyusha is also writing notes, Nisha is also writing notes. Excellent. Making your own notes is the best way to learn. Making your own notes is the best way to learn. Another good way to learn is by motivating your students, by liking the session that you are attending. Because if you are liking the session, the like should be visible in the video likes. All right. So if 15 students are watching and there are only 10 likes, that doesn't make any sense. Okay, I'm very good at maths. So I know that there are some students who have not liked it. So make sure that you like this session. Make sure that you like this session. All right. Liked, shared also. Okay, great. Okay, fine. So wave functions of a 2D rotor, particle on a ring. Wave functions of a 2D rotor, particle on a ring. Okay. Now, what is a particle on the ring? What is a particle on the ring? Just like if you remember, particle in a box. Okay, particle in a one-dimensional box. What did we imagine? We imagined something, an ant on a floating stick of wood, an ant on a floating matchstick. That's what a particle in a box was, one-dimensional box. Now here, what is a particle on a ring? Imagine something that is just moving along a circular track. Something that is just moving along a circular track. That is a particle on a ring. Okay, something that is moving along a circular track. that is a particle on a ring. Okay, now its wave function comes out to be 1 over root of 2 pi e raised to I m pi. 1 over root of 2 pi e raised to I m pi. Okay, so this is a very important wave function. Okay, any example? Yes, there are many examples. One of the examples that you can assume is benzene itself. Okay, benzene has a circular delocalized electron structure. Okay, circular delocalized electron structure. Yes, Earth rotating around the sun is also kind of a particle on a ring. Okay, Earth rotating around the sun is also a particle on a ring. All right, benzene molecule is also a particle on a ring. Okay, benzene molecule is also a particle on a ring. Benzene molecule is also a particle on a ring. There are electrons which are delocalized along the benzene molecule. CH3 is not a ring. Okay, CH3 there is no delocalization of electrons there. So if electrons are delocalized, only then we can consider a particle on a ring. Okay, if electrons are delocalized, only then you can have a particle on a ring. But you can have more interesting examples also. Like for example, you can have something like this. You can have 6 benzene rings fused to each other. Okay, you can have 6 benzene rings fused to each other with electrons delocalized. And conjugated systems. Okay, delocalized electrons and conjugated systems. Can someone tell me what this is? Can someone tell me what this molecule is? Okay, there are 7 benzene rings that are fused with each other. So can someone tell me what this system is? Okay, this system can be assumed to be a particle on a ring. Okay, this system can be assumed to be a particle on a ring. Okay, does someone know what this is? Does someone know the name of this molecule? Those who have attended aromaticity or GOC might know this. This is called as coronene. And this is benzene. One is called as coronene, the other is called as benzene. Okay, one is called as coronene, the other is called as benzene. Okay, is this clear? So helical molecules are not particle on the ring. Electrons in orbits are particles on the ring, but electrons are not really in orbits. Electrons are not really rotating around the nucleus. Electrons have a probability distribution, probability density around the nucleus, which we will study when we look at hydrogen atoms. We will study that also. Okay, when we will look at hydrogen atoms, we will study that also. Okay, so this is a particle in a two-dimensional particle on a two-dimensional rigid rotor. Particle on a sorry, Faye and Say, what is that? FAYE and what is SAYE? What does that mean? Value of m for this equation. Very good, very good. That's the new point. 0, plus minus 1, plus minus 2, plus minus 3, and so on. Okay? Plus means anti-clockwise rotation. Anti-clockwise rotation means plus. Minus means clockwise rotation. minus means clockwise rotation. Okay, minus means clockwise rotation. That is what this means. Okay, phi and psi, what? Oh, I understand what you mean. Phi, if you look at this, okay, phi is the angle made with the x-axis and theta is the angle made with the z-axis. Okay, phi is the angle made with the x-axis, theta is the angle made with the z-axis, whereas psi is the wave function. Psi is the wave function. Okay, this is the wave function of a two-dimensional rotor. This wave function actually tells you what is the probability of finding the electron or the particle in that particular ring. Okay, it tells you. So it's not phi and psi. What it is spelled like this. This is psi and this is phi. Okay, psi and phi, they are both Greek letters. Both of them are Greek letters. Psi is used to actually denote the wave function. Phi is used to denote an angle. Sometime later we are also going to use phi to denote a wave function. All right, Nadeem sir started chemical bonding. Nadeem sir finished chemical bonding. All right, Nadeem sir has already completed chemical bonding. Bhakti. So all his lectures are available on the channel. Just go and check them out. Okay. All right. So value for m in this particular equation. What is the value of m in this particular equation? Value of m is 0, plus minus 1, plus minus 2, plus minus 3. What is m? M is the rotational quantum number. M is the rotational quantum number. M is the rotational quantum number. Okay, but this is a rotational quantum number for a two-dimensional rigid rotor. Okay, this is a rotational quantum number for a two-dimensional rigid rotor specifically. Okay, this is a rotational quantum number for a two-dimensional rigid rotor specifically. Okay, got it? Now, what does this wave function actually tell you? What is the meaning of this wave function? Before we go there, let me remind you that on popular demand, we have extended the 70% flat off offer. Okay, promo code is ITIHAS. Remember, promo code is ITIHAS. The flat 70% offer has been extended, but we don't know up till what time this will be extended. So if you are interested in enrolling, enroll now. Okay, if you are interested in enrolling, enroll now. Okay. Jazwa batch when started? That's classes already completed. Yes, classes are already completed. Correct. Okay. Now this offer is only there for 3 days, 3 more days. All right. So we don't know if you will be able to register because there are only limited seats. Okay. If these seats get filled up, we won't be able to give more 70% discount. All right. So don't even wait for these 3 days to be completed. Register immediately, enroll immediately if you can. Okay, and where do you want to enroll? There is an English batch that is going on. It has started on the 17th of October. If you want to enroll in the Hindi version live batch, that batch has also started on this Wednesday itself. Okay, that batch has started on this Wednesday itself. Only 2 lectures are complete in that batch, so you are not going to fall behind. Organic chemistry is going to start tomorrow morning. All right, organic chemistry is going to start tomorrow morning. And you can register immediately and you will not have missed a lot of the syllabus. You will be able to cover the entire syllabus. Okay. Plus, if you are weak in physical chemistry, or even if you are strong in physical chemistry and want to practice more, the physical chemistry concept check books are one of the best books that you can have in your arsenal. All right. These are books with more than 3000 practice questions. All right. And if you solve all of these practice questions, you will be prepared, well prepared for not just CSIR NET, but GATE, TIFR, SET, BARC, ONGC, DRDO and NTPC exams. You will be well prepared for all of these entrance exams. All right, you don't have to study from anywhere else. You don't have to refer a reference book. These books are sufficient. Okay. And especially we are offering these books at a heavy 300 rupee discount. These books are available at only 500 rupees right now. Okay, so 795 is the actual cost. We are giving a flat 300 rupee discount, almost 300 rupee discount, and these books are available at 500 rupees only. So if you are interested in purchasing these books, purchase them today. Okay, do not waste time, immediately order them so that you can start practicing from one of the best books in the market. Okay, all right, now what do these wave functions mean? What do these wave functions mean? These wave functions, so e raised to I m phi, what this actually means is cos of m phi plus I sin of m phi. Okay, cos of m phi plus I sin of m phi. Okay, now both of these functions, cos and sine, both of these are oscillating functions. Both of these are oscillating functions, which means when you try to plot the wave function, you will get an oscillation. You will get a wave-like form. Okay, you will get an oscillation. You will get a wave-like form. All right. Now let's try to plot these wave functions. Let's try to plot these wave functions. Now what will happen is, the wave function that you are plotting, the wave function has to start and end at the same point. Okay, which means if the wave function starts from here, it also has to end here. It also has to end here. Okay, so as a result, if it is an oscillating wave function, it needs to have a finite number of waves and an integer number of waves. So for example, you will have wave number 1, you will have wave number 2, you will have wave number 3, and you will have wave number 4. Okay, so there are 4 waves in this wave function, which is why it starts at a certain point, it also ends at the same point. And this is necessary because wave functions must be continuous. Wave functions must be continuous. Okay, this is one of the requirements of any wave function. All wave functions must be continuous. Okay, all wave functions must be continuous, which is why you should have an integer number of waves. And as a result, if you look at this entire circumference, this should have an integer number of waves. This should have an integer number of waves. Okay, and this lambda can also be written as h upon p. Okay, the lambda here can also be written as h upon p. All right, so which is why at the end of the day, when you solve this, what you will get is mvr, or the angular momentum, that is equal to mh upon 2 pi, and because of this m, what you can say is that the angular momentum is quantized. Angular momentum is also quantized. It's not just energies, but there are other properties like angular momentum which also are quantized. And if you remember, this was mentioned in the Bohr's theory. If you remember your 11th and class 11 and class 12 chemistry, angular momentum is quantized is mentioned in Bohr's theory. Okay, angular momentum is quantized is mentioned in Bohr's theory. What is net probability? Net probability is 1. Okay, net probability always has to be 1. Okay, net probability always has to be 1, and which is why there is that root of 1 over 2 pi. That root of 1 upon 2 pi ensures that the net probability is 1. Okay, Lambda is the wavelength of this particular wave. Okay, it is a wave function, so it's the wavelength of that particular wave. Got it? Got it? So essentially we get quantized angular momentum if we apply the Schrodinger equation to Bohr's theory, to a rigid rotor. Okay, got it? Understood, everyone? Is this clear to all of you? Is this clear to all of you? Is this clear to all of you? Okay, okay. So these were the wave functions. So the wave functions of a rigid rotor are oscillating wave functions. Of a 2D rigid rotor, they are oscillating wave functions, but oscillating wave functions in such a way that there are an integer number of wavelengths along the circumference or along the ring. Okay, so what is the energy now? What are the energies? What are the energies of 2D rotors? What are the energies of 2D rotors? Okay, what are the energies of 2D rotors? Can someone tell me? So here the quantum number is m. So the energy comes out to be m square h cross square upon 2 m r square. Okay, m square h cross square upon 2 m r square. This small m is the quantum number, and its values are 0, plus minus 1, plus minus 2, and so on. Okay, its values are 0, plus minus 1, and plus minus 2, and so on. Whereas capital M and capital R, these are mass and radius of well, let's not write them together. M is the mass of rotor. Okay, mass of rotor meaning there is a particle which is rotating around an axis. Okay, there is a particle which is rotating around an axis, and that is the mass of a rotor. Capital R is the radius of rotation. Radius of rotation or radius of the ring. Okay, note that this is not the radius of the particle that is rotating. This is the radius of its path. Its circular path has a radius capital R. Okay, the circular path has a radius capital R. Okay, is that clear? Is that clear to all of you? All right, is that clear to all of you? Okay, great. Okay, so this is the energy of a 2D rotor. Okay, this is the energy of a 2D rotor. Now if we calculate the energies, if m is equal to 0, this energy will simply be 0, because 0 square into h cross square upon 2mr square. Okay, E plus 1, this will be plus 1 square h cross square upon 2mr square, meaning simply h cross square upon 2mr square. Okay, h cross square upon 2mr square. Okay, how about E minus 1? Now E minus 1 also is minus 1 square h cross square upon 2mr square, and the square of minus 1, make a note of this, square of minus 1 is also plus 1. Square of minus 1 is also plus 1, just like the square of plus 1. So this also comes out to be not minus h cross square but plus h cross square upon 2mr square. And notice that these two are actually equal. Notice that these two are actually equal. Okay, notice that these two are actually equal. Okay, is this clear? Is this clear to all of you? Is this clear to all of you? Is this clear to all of you? So if they are equal, what that means is as Em is proportional to m square, okay, because h cross square upon 2mr square, they are all the same, as it is proportional to m square for, so E plus 2 will be equal to E minus 2, E plus 3 will be equal to E minus 3, because the square of 2 and the square of minus 2, they are the same. The square of 3 and the square of minus 3, they are the same. What that means is the energy is going to be degenerate. Okay, you are going to see degeneracy in the energy level. So how do the energy levels actually look like? How do the energy levels actually look like? So the ground state has E0 equal to 0. Ground state has E0 equal to 0. First excited state has two energy levels, one for plus 1, one for minus 1. Okay. Second excited state also has two energy levels, plus 2, minus 2. Third excited state also has two energy levels, plus 3, minus 3, and so on. Okay. What that means is ground state degeneracy is 1. Okay, ground state degeneracy is 1. But for all of the excited states, degeneracy is equal to 2. Okay, degeneracy is equal to 2 for all of the excited states. And this is only for a 2D rotor. Remember, this is only for a 2D rotor. For a 3-dimensional rotor, which we are going to study in the next class, this degeneracy has a more complicated expression. Okay, is this clear to all of you? So as an exercise, calculate energy required, or calculate the wavelength required for the HOMO-LUMO transition. HOMO-LUMO transition for benzene. HOMO-LUMO transition for benzene. Okay, all of us know what benzene is. We can assume 2D rotor. We can assume the 2D rotor model. Okay, what we can do is we can assume the 2D rotor model. Okay, now for calculating this, or for treating this like a 2D rotor, the radius is approximately 1.5 angstroms. The mass of an electron is 9.1 into 10 raised to minus 31 kg. Mass of an electron is 9.1 into 10 raised to minus 31 kg. Okay, and h, which is the Planck's constant, that's 6.626 into 10 raised to minus 34 joules seconds. Okay, this is what is given to us. Okay, this is what is already known to us. So what we are going to try to do is, because we can treat benzene, okay, like a particle on a ring system. Let's use a different color here. Because we can treat benzene as a particle on a ring, let's calculate the HOMO-LUMO transition. Now, what are the HOMO and the LUMO? Okay, so if you look at benzene has 6 pi electrons. right? Benzene has 6 pi electrons. Okay, so if the energy level diagram was this, m equal to 0, m equal to -1, m equal to +1, m equal to -2, m equal to +2. Can someone tell me, if I start distributing these 6 pi electrons in this energy level diagram, how many unpaired electrons are we going to get? Can someone tell me how many unpaired electrons are we going to get if we distribute 6 pi electrons there? Can someone tell me how many unpaired electrons we are going to get if you start distributing 6 pi electrons on this system? All right, yes, absolutely. We are going to get 0 unpaired electrons. Why? Because 1, 2, 3, 4, 5 and 6. All 6 electrons will go there. And what this tells us is that this is the HOMO, highest occupied molecular orbital, and this is the LUMO. Okay, HOMO and LUMO, which means the transition that we want to calculate is the transition from this point. Okay, it is the transition from this level to there. M equal to +1 or -1 to m equal to +2 or -2. Okay, that is the transition that we want to calculate. So HOMO-LUMO transition is something like this. Okay, so now what we can write is, for HOMO, highest occupied molecular orbital, mod of m is equal to 1, and for LUMO, lowest unoccupied molecular orbital, mod of m is equal to 2. So HOMO-LUMO transition will take place from mod m equal to 1 to mod m equal to 2. Okay, so therefore delta E, which will be hc upon lambda, that's the wavelength that we want to calculate. hc upon lambda, that's the wavelength that we want to calculate, and this comes out to be m LUMO squared minus m HOMO squared into h cross square upon 2 m r squared. Okay, and that's what we want to calculate. What is m LUMO? M LUMO is 2, so that's 2 square minus, this will be 1 squared, into h cross is actually, how much is h cross? H cross is h upon 4 pi. Okay, h cross is h upon, sorry, not 4 pi, h upon 2 pi. H cross is h upon 2 pi. So when you actually simplify this, what you will get is h square upon 8 pi square m r square. Okay, because square of 2 pi is 4 pi square, that 4 gets multiplied with this 2 to get an 8 pi square m r square. Okay, so essentially hc upon lambda is 3 h square upon 8 pi square m r square. Okay, so hang on, let me just make some space. So therefore what we have is hc upon lambda is equal to 3 h square upon 8 pi square m r square, and there are quantities that will get cancelled off. So for example, this h will get cancelled off with that h, and if you want to calculate lambda now, therefore lambda, now just start cross multiplying. Lambda is 8 pi square m r square into c upon 3h. So let's substitute these values. 8 into 3.14 squared into mass is 9.1 into 10 raised to minus 31 into r squared. R was 1.5 angstrom, so let's convert it to meters, square of that, and c is 3 into 10 raised to 8, which is the speed of light. That entire thing gets divided by 3 into 6.62 into 10 raised to minus 34. Okay, so go ahead, calculate this, and the answer that you are going to get is going to be in meters. The answer that you are going to get is going to be in meters, Let's calculate this. So can someone tell me what the answer is going to be? Can someone tell me what the answer is going to be? What is the answer going to be? What is the answer going to be? What is the answer going to be? Can someone tell me what the answer is going to be? I'll give you a hint. I will give you a hint. You will get 10 raised to minus 7. You will get 10 raised to minus 7 if you write the answer in meters. You will get 10 raised to minus 7 if you write the answer in meters. Okay, you will get the answer in meters if you write 10 raised to minus if you calculate the answer in meters, you will get 10 raised to minus 7. Okay, can someone tell me what the answer would be? Let's see if you can calculate this. 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 15.3, no, check again. Not 15.3. It will be 2.44 into 10 raised to minus 7. Okay, it will be 2.44. Yeah, close to 2. 2.44 into 10 raised to minus 7. Even if you get 2.09, I understand. You must have approximated somewhere. You must have approximated somewhere. The answer that you will get is 2.44 into 10 raised to minus 7, which in nanometers is 244 nanometers, which in nanometers is 244 nanometers. Okay, this is the wavelength predicted for absorption. This is the wavelength of light that is predicted for benzene. Okay, this is the wavelength of light predicted for benzene. Okay, this is the wavelength of light predicted for benzene. Okay, and if you actually observe, do you remember where benzene absorbs? Which color does benzene actually absorb? Or which wavelength does benzene absorb? If you remember Woodward-Fieser rules, what is the base wavelength? In Woodward-Fieser rules, what is the base wavelength of absorption? It's in UV, but can you tell me what the exact wavelength is? What is the exact actual value? In UV, I understand that, but what is the exact value? Do you remember? 214? I don't think it's 214. I am talking about the base value without any side chains, without any substituents. Basic benzene absorption. Basic benzene absorption. Where is the benzene absorption? Not 214, not 250. Usually, benzene absorption is close to 190 nanometers. Okay, this is the observed value. This is the observed value. Okay, this is the observed value. All right, this is the observed value. So it is close to 190 nanometers. So you can see how close we are. Okay, so benzene is not really like a particle in a box system, a pen or a particle on the ring system. Benzene is a much more complicated system where there is delocalization, and due to delocalization there is a reduction in energy, there is a resonance, and in spite of all of that, we are not even considering all those factors, and look how close we are. The power of 10 is accurate, 10 raised to minus 9 meters. Okay, so even after approximating this as a particle on a ring, we are still getting a very, very close value. Okay, all right. So this was particle on a ring. This was the rigid rotor. Okay, And let me remind you again of this particular promo code, which is only valid for 3 more days. Do not waste time because there are only limited seats available. Do not waste time because only limited seats are available. Make sure that you enroll today in whichever course that you want, CSIR NET, GATE, or even SET courses. Okay, whichever course that you want, CSIR NET, GATE, or SET courses. All right, and remember that from 17th of October, the English version of the CSIR NET batch has already started. Okay, the English version of the CSIR NET batch has already started from 17th of October. Enroll today. You haven't missed a lot. Only a few lectures have happened. Okay, only a few lectures have happened. So if you're interested in the complete structured CSIR NET course, enroll today. All right. And if any of you are interested in our classroom batch is also starting on the 1st of November. Okay, our classroom batch is also starting on the 1st of November. This batch is going to be held in Pune and Jodhpur centers. Okay, this batch is going to be there in Pune and Jodhpur centers. All right, so don't waste any more time, because if you start preparing right now, this is the perfect time to actually enhance your preparation as compared to anyone whom you are competing with. Okay, so let's stop today's session here. We will continue tomorrow again with a 3D rigid rotor. Okay, we will continue tomorrow again with the 3D rigid rotor. Okay, because the 3D rigid rotor is more useful, especially when we are talking about rotational spectroscopy. The 3D rigid rotor is essentially what we are talking about. Okay, so all the parts that are going to be useful for rotational spectroscopy we are going to discuss in the next class. So if you attend the next class, you are not just covering rigid rotor from quantum mechanics point of view, quantum chemistry point of view, but you are also getting the basics of rotational spectra or microwave spectra. Okay, so let's stop this class here today, and we will continue tomorrow with another session of quantum chemistry. All right, so goodbye everyone, and happy learning.